we've got an exam coming up Thursday night. Okay, keep reminding you, 6:30 to 8:30, and I think there's sufficient room in C1, so we don't have to worry about alphabetizing stuff. So it'll be in the room next door. When you come in on Thursday night, the papers will be set apart alphabetically, and it'll kind of start with A's at the front and Z's up at the back, sort of moving up that way. So just to give you an idea of where to look. There's a handout floating around. Anybody up there not have one? Need one? Okay. Now, yesterday, kind of left off with playing a game quite rapidly that was a particular kind of coordination game. And there's a couple of ideas that I want you to get out of this this idea of coordination. I mean, it's an important kind of strategic problem, how to get people to sort of work together, okay? And the idea is that specialized players or people can do specific tasks, and they produce things together in some way. But often the output depends upon how much effort the various people are putting in, okay? And so we've got this little theory, this particular game, a minimum effort game, where it says, look, people are going to work together, they're going to get a joint payoff, but the joint payoff is going to depend upon how much effort they put in. And the effort, the way in which the two bits of effort go together is that, you know, if Jason puts in some effort and I put in some effort and they're the same amount of effort, then we get a payoff. If I work a little bit harder, it doesn't increase the payoff because Jason needs to work a little bit harder to actually get the total payoff going. That's one aspect. And the other thing is if I work a little bit harder, it costs me. Okay, it's like my effort. And so if I don't get any extra payoff, I am getting an extra cost. So that's kind of a negative from my standpoint. So when you're thinking about the strategic interaction, we're trying to think about the incentives of people to work together. So I set this game up yesterday, and I actually got some of the cells wrong. I don't know if you've been playing around with it, but I made a few little mistakes, which I corrected last night. And the table that I've handed out today is a little bit different. I'm going to make a game a little bit simpler, and everything in that table, if you add the number 2 to every one of those numbers, you'll come up with the correct table that we should have had yesterday. Okay, but let's just work with this little simpler idea. So, just very quickly, here's the table we had yesterday, sort of. But I corrected it. Along the diagonal is pretty easy to work out, okay, because that's when everybody works the same amount. And so if nobody works at all, we get this fixed payment of 2 each, which is what we had over here with the little arrows pointing. And then if each player puts in 1 level of effort, it goes to 3. They put in 2 level of effort, the net payoff goes to 4. Net payoff 5, net payoff 6. So these are kind of the gains to working together cooperatively. Don't worry about writing this down. I mean, we're not going to work with this one. We'll work with the one on the other page, okay? And then similarly, as you go along these rows or columns, you've got to think about the payoffs to each of the players as each of them puts in more, as each of them changes their effort levels. But it got a little confusing thinking, for me at least, and probably for you, thinking about the payoffs because, you know, I gave you 4. Everybody gets 2 anyhow, no matter what effort level I put on. You got to worry about how much your cost of effort is. You got to worry about how much the extra benefit is. A lot of 4 things going on there. So I tried to simplify it a little bit, and let's get rid of the fixed payment of 2 and start with this particular table. Okay. Now, again, we're going to start. We're going to start off with an endowment of $4 each, and let's run through the table before I hand out the money so you get an idea of what you're doing. I think there was one guy yesterday who was, you know, he really didn't know what to do, so just took a punt on 1, and there's another player put in 4, so the minimum, or had an effort level of 4, so the minimum level of effort was 1, okay? And then we had a 0 and a 4 for our other pairing, okay? But let's just go over this. Let's go over this table again, okay? When you're reading a payoff table, you sort of look at it and you think, well, how many strategies or choices does the red player have? Well, there's 5. They can put in no effort, 1 unit of effort, 2 units of effort, 3 units of effort, 4 units of effort. Similarly, the blue player can put in 0 units of effort, 1, 2, 3, and 4. Okay, so that's what they can do. And we're assuming this is a game of complete information, so everybody knows what this payoff table is. You guys are working together. You know what the outputs are. You know what the costs of effort are for each person. Okay. So if nobody works, that is, the red player chooses 0 and the blue player chooses 0, okay, then there's no cost of effort, but there's also no joint payoff. Okay, and so they each get zeros. Now let's suppose that we go along the diagonal first. And we think, well, supposing the blue player puts in 1 unit of effort and the red player puts in 1 unit of effort, then we want to look at their payoffs. Well, according to these little formulas, and our intuitive idea is that a unit of effort costs 1 10-cent piece, okay? And what do you get back? You get, or if you like, you can think of it as $1, okay, but it's really only a tenth of $1, okay? So what do you get back? Well, the joint production process, if you both cooperate and you both put in 1 unit of effort, you get $2 each, okay? So your net payoff is the 2 minus the 1, which is 1 for blue, 1 for red. Similarly, if you increase the effort level by 1 again, then you get an extra 2, but you've got to subtract off the cost of the effort levels for each person, which is 1, so the payoff goes up by 1, going from this coordinated effort level of 2 each to the coordinated effort level of 3 each. Again, what happens is moving from here to here, because you're both improving the minimum effort level from 2 to 3, you're going to get a total of 6, the payoff of 6, but the effort levels have gone up now to a size of 3, and each of those effort levels costs $1, so we get a payoff of 3, and then similarly from 3 to 4. Okay, got that idea? So going along the diagonal is, if you like, the gains from coordinated effort together. Now that's one of the key ideas, is that in these kind of games, there are benefits to individual players from coordinating their efforts together. Now we want to see, are they going to be able to realize these benefits? Okay, because there's also some other risks in this game. Yep. It's 2 times whichever one is smallest. So the idea, what I'm putting in these brackets here, is that let's look at any cell. Let's look at the effort levels. Okay, so let's pick this cell here. Okay, the effort level there is 1 for red and 3 for blue. The minimum effort is the smallest one. So we take 2 times the minimum effort. Does that help? So that's the basic way to think about each of the payoffs, is that there are various combinations of efforts, but it's kind of like if I'm working 1 and you're working 1, then we're going to get, the minimum effort is 1, and we're going to get an output of 2. But if you start working more and more and more, it's not increasing the minimum effort level because I haven't done anything extra. So that's the kind of intuitive idea, is that your extra efforts, they're going to cost you, but they're not going to bring any benefit to anybody because the minimum stays the same. Is that okay? Good question. Okay, yeah. I mean, with a lot of these, things, we're just using the theory to kind of help us keep track of the basics of the game. Okay, and the basics are how much effort are people going to put in, and then what are their payoffs in putting in these effort. And there's kind of a payoff. Jointly they can work together, but they have to work together to get the payoff. But kind of privately, they're going to be paying their own cost if they increase their effort. Okay, so let's look across a row. Okay, we're going to go across a row. Let's take this row where the red level. So the red player chooses 2, okay, for their effort level. And we know if the blue player chooses 2, so we have an effort level of 2 here and an effort level of 2 there, that the minimum effort level is 2, and so that gives them $4 jointly, but the net payoff has got to subtract off the cost, and if each of them is putting in 2 units of effort, then there's $2 of cost from each of them. So we'd have 4 minus 2 is 2, and that gives us that joint payoff of 2 and 2. That's what we're looking at the diagonals. Okay? Now let's imagine moving along the row this way or this way. From this cell, let's first think of moving to the left. Now what's moving to the left? Moving to the left, we're staying in the same row, so red player is not changing their effort level. It's staying at 2. What we're doing when we move to the left here is we're increasing blue's effort level from 2 to 3. So blue's effort level goes up. Red stays the same. The minimum stays the same. So the minimum is still 2. So the payoff to each of them is, the benefit from the output is 4 each. But now the blue player's effort level has gone up to 3. So we want to subtract off $3 of cost for him from his 4, so that's why his number drops down to 1. His payoff drops down to 1. The red players hasn't changed their effort levels. The minimum effort level hasn't changed, so the total output is the same. He's still getting the $2. So from the red player's standpoint, there's no change in his payoff. Okay, let's keep going to the left. It means that when we're going to the left, it means the blue player is increasing their effort level even more. Okay, what happens? Well, an extra unit of effort costs the blue player 1, but it doesn't create any benefit because the minimum hasn't changed. The minimum is still 2. At the cell 2 and 4, the minimum effort level is still 2. The blue player is working away like crazy at 4. It's costing him, but he's not getting any extra benefit. So compared to where we start out with, going from here to here is a cost of 1. Going from here to here is a cost of 1. His payoffs are going down. Okay? And similarly, if we go, let's imagine if we go to the right along the row. Okay, so we're sitting here. Everybody's cooperating 2 and 2 for the blue player, 2 for the blue player, 2 for the red player. We're trying to think what happens if we move to the right along a row. Well, along a row, the red player's effort level is not changing. So the red player's effort level is not changing, but the blue player's is. The blue player's is going down. Now notice what happens here. When the blue player's effort level goes down, it drops the minimum effort level to 1. Okay. So it also affects the red payoff as well as his own payoff. Remember, when we are starting from here, we move to the left, increasing your effort levels as a blue player cost you, but it didn't hurt the other guy. Whereas starting from here, going to the right, it does hurt the other guy. You're dropping the minimum effort level. You're dropping it to 1, so your payoff is going down by 2, but your costs have gone down only by 1, so that's a net reduction for you, okay, to 1. So you've lost some payoff here. Let's say you keep going, you keep dropping your effort level, you don't work at all, you drop it to 0, okay? That means the minimum effort level is 0. You don't face any costs, but you don't get any benefits. As a matter of fact, nobody gets any benefits. The red guy actually loses because he's still working at 2, if he is working at 2, and you're only working at 0, the minimum is 0, you're not getting any joint output. The red guy's losing his $2 of cost. If you like, the cost of the effort. Is that okay? Reading across? Jason, you okay with that? Okay, so the idea is he's reading across each row. Now, we can use that same kind of reasoning to figure out what's the best response of the blue player to anything that the red player would do. Well, let's take this, we're using x's. So if we put an x here, that's the best response for the blue player. It's the highest number. 2 is higher than 1 is higher than 0. 2 is higher than 1 is higher than 0. For when the red player puts an effort level of 2. Well, the similar kind of reasoning is going to hold for the best responses of the blue player to the red player is playing 3. Again, 3 is higher than 2, 3 is higher than 2, is higher than 1, is higher than 0. Okay. Let's keep going here to the right. Supposing everybody is working full on, okay? They're all putting in the great effort. They each put in 4 units of effort. The minimum is 4. The total output is for each person is going to be 8. So they subtract from 8 minus the $8 they get minus the 4 cost of effort gives them a net payment of 4 each. Now what happens is the blue player lowers his effort. Well, he goes down to, his benefits go down to 3, go down to 2, go down to 1, go down to 0. So again, 4 is the best response, okay? Sorry. I have no idea what's happening here. I think I'm just tracing this guy out here. So I'm just going to finish putting the best responses for the blue player in these cells. Again, you want to go back and think through, why is this blue a best, why is 1, an effort level of 1, a best response if the other guy chooses 1? Well, that's because if you match what he does, you get a payoff of 1. But if you don't match, like you slack off, you're going to get a payoff of 0. And if you work too hard, you're going to get a payoff of 0, and then even some negative payoffs if you work more and more. Okay? So the best response is always to match the effort level of the other player. It's a symmetric game. Now, often in your reasoning, like supposing I was asked this kind of thing on an exam, okay, and I was saying, explain the pattern of the best responses. Well, if you do it for the blue player, and you could say, well, the whole thing's symmetric, so you could say the same kind of reasoning applies to the red player. That's the easy way out, okay? As long as you explain it clearly for the blue player, then it's everything symmetric for the red player. So let's have a put the best responses in for the red player, and then let me just tack them in, and we will then make sure that we're interpreting them properly, okay? What's the best response? Well, let's suppose that we look down any column like this. So we're looking down a column. Looking down a column is looking down a choice, is fixing the choice of the blue player at 3. Okay, the effort level is 3. Well, our intuition is you want to match the other guy's effort level. That's going to give you your best response. So the red player, he gets a payoff of 3 by matching to 3. If he increases it beyond 3, it doesn't change the minimum at all. So his extra effort costs him, if you like. He doesn't get any extra benefit, so he drops down 1. On the other hand, if he slacks off, he also reduces the minimum payment, and he loses 2, okay? And he does have a savings in costs, but in net he goes down by 1. Okay, so this goes down from 3 down to 2. So 3 is better than 2, 3 is better than 1, 3 is better than 0. And similarly for any particular column. Okay? Those are the patterns of mutual best responses. And so intuitively we'd say in this game, the best strategies to play will always be one that match the other player's strategies. And every one of those diagonal cells, or the strategies in the diagonal cells, would be a Nash equilibrium. So we have a game that's a game with many Nash equilibria, or multiple Nash equilibria. Now, just before we kind of go on with this, anybody got any questions about interpreting? Like, if I put this table on the exam, okay, and I'd say, identify the Nash equilibrium and explain your reasoning. Could do it? Yep. What does it look like to you? Okay. Well, there's only one that has the highest joint payoff. There's a cell that has the highest joint payoff, 4 and 4, right? Okay, and we're saying that is a Nash equilibria. But the reason it's a Nash equilibria, it's because the blue player is saying, if both players expect it, okay, if I'm working 4, you're working 4, you expect me to work 4, I expect you to work 4, then I'm thinking, okay, the best thing for me to do if you're working 4 is to match what you do, because if I slack off, then I'm going to be reducing the minimum, and yeah, I'll save a little bit of cost, but also lose some output. That's not good for me. And the same reasoning would apply to you. We're each making a mutual best response. That's why 4 and 4 is a Nash equilibrium. Okay, but 3 and 3 is a Nash equilibrium too. Okay, is 4 and 4 a dominant strategy equilibrium? What do you think? Can't be. What were you thinking? Well, I mean, shook your head. It's what. Yep. Okay. The question was, is it a dominant strategy equilibrium? And the reasoning that, what was your name? Tom. And what was your name? Nathaniel. Okay, Nathaniel and Tom are sitting there. Tom didn't really answer Nathaniel's question. What Tom did was looked at the cell 2 and 2 and explained the payoffs there, and he looked at the cell 4 and 4 and explained the payoff. But for a dominant strategy, what you would need is those X's for the blue guys to be all lined up going across one row, the blue X's, okay? Or for the red player, the best response would be, wouldn't matter what you do, okay? So they'd be all the zeros would be down one column. So the dominant strategy is a strategy it's a particular strategy that's best no matter what anybody else does. But in this game, the best strategy to do does depend on what the other player does. It's the best strategy for me depends upon what you do, and the best strategy for you depends on what I do. In particular, you should match what I do, and I should match what you do. And the 5 diagonals give you we have this every time, don't we? Let me see if I can get rid of this. I should do this. I'm going to do this next time before I come to class, okay, and get rid of the thing. Now, so Nathaniel, are you happy with the idea of why it's not a dominant strategy? Okay, a dominant strategy. This best response analysis is always, in some sense, it's the best way to go in terms of figuring out what the theory would predict what's going to happen in a game. Okay, where you're looking, so you got your payoff matrix, and you're looking down each row, trying to find the maximum for the red player going down there. Looking across, looking down each column, finding the maximum for the red player. Looking across each row, finding the maximum for the blue player, and you just kind of do it mechanically at the beginning until you get the pattern of X's O's. Then you look for the mutual best responses. That identifies all the Nash equilibria. So that's always, at least whether it's a multi-choice question or you're just thinking about something, sketching something down, the idea is to look for the patterns of mutual best responses. There happen to be 5 here. So there's 5 Nash equilibria. Yes? Okay, good question. Question is, given that it's a simultaneous game, and we're using Nash equilibriums to make our predictions, we now have 5 different things we could predict. Okay, so what are the predictions of game theory? Well, one of the things about predicting is often you don't narrow it down definitely, but you do reduce the possibilities. Okay, at least that's one way to think about Nash equilibria. So if someone was to say here, well, I think one player is going to work really hard and the other guy is going to slack off, that's what I would predict. And you could say, well, okay, you could think that, but it's not a prediction of the theory because 0 and 4 isn't a Nash equilibria. Okay, so it's kind of like I can rule out lots of other different combinations, but I can't really narrow down here. Megan. Megan sort of saying, wouldn't you have to look for some kind of focal point? Good thought. If you had if say you were playing against Nathaniel, you don't know one another, you never met before and like that, he's got to figure something out, you got to figure something out. What focal point would you think about? Whether I think you'd work hard or not. And Nathaniel, you got an intuition about the focal point thing? You'd go for the greatest payoffs, okay? So if you're playing against Nathaniel, and he's the kind of guy that always goes for the greatest payoffs. I mean, he can see all of these cells, but if he's going to go for the greatest payoffs, you could expect him to do that. Then which would you do? I'd try to match that, right? Okay. But Nathaniel, what if you weren't so sure that Megan was the kind of person, that she's not the kind of girl that always goes for the greatest payoffs? Okay. So you're sitting here thinking, well, I really don't know. I'm blue guy. If I go for the greatest payoffs, I'm going to get 4. But if Megan is kind of, she's fudging a little bit here, I might get 2, or I might get 0, I might get -2, I might get -4. If she decides not to work at all, and it's thinking, well, maybe she won't be thinking that I'm the kind of guy that goes for the best payoffs. It's kind of risky for me to go for the best payoffs if I'm the blue player. It's not risky if you can believe the other person's going to focus in on that one, okay? But what if you can't? What if they're thinking, oh, this is a difficult game, I'm just going to do the minimum thing here and make sure that I get, I don't get any big costs because there's some big negative numbers here. Matter of fact, why don't we just do this and play it? Now, I'm going to play it a little differently than we did yesterday, okay? Morgan, I haven't involved you yet. Morgan, you got an endowment. Now look at the endowment. It's just so that you walk away with this endowment, okay? It's like, so that if you have to pay something for your effort, okay, Nathaniel, you can do it. Actually, I don't want Nathaniel to do it. I'd like to because he participated, but I don't want people to think he's always because he's already stated once he's the kind of guy that always plays 4. Okay, what I want you to do is, and he may be, he may not be. Okay, but I don't want him to think. I don't want you to know for sure what Nathaniel's going to do. The idea is you're sitting here looking at payoffs and trying to figure out what to do. What's your name? Tara. Okay, Tara, you've got an endowment of 4. Now, again, the 4 is just to cover any cost that you have. If you don't have any costs, then it'll work out all right. What's your name? Amanda. And, whoops, dropped one. What's your name? Justin. Amanda, Justin, Tara, and Morgan. That was me, right? Okay, now, so we have 4 people playing this game. Now, yesterday what I did is I paired you up. But now I'm not going to pair you up. I'm going to ask you to make a choice, and all 4 of you are going to have to choose an effort level. Okay? So the idea isn't just a 2-player game, it's a 4-player game. But the payoffs are basically going to be the same. And like supposing you're sitting there as Morgan, and Morgan's a red player, and he's trying to think about what Amanda's up there, Tara's over here, and Justin's up there, what they're going to do, okay? So you're trying to think about what they're going to do, and there's 3 other players you got to think about. But the real key for your payoff isn't so much what each of them does, it's what the minimum of what they do is, okay? Because the joint output is going to be determined by the minimum effort level of the 4 of you. Instead of just having minimum of all these guys, you can sort of think as, well, the blue players are everybody else, and this is the minimum of, if the minimum of everybody else is 4, or the minimum of everybody else is 3, or the minimum of everybody else is 2, or the minimum of everybody else is 1, or the minimum of everyone else is 0, okay? So then you could figure out what your payoffs are. And you might be trying to think, well, I wonder what to expect about what the minimum level of everybody else is going to be. You've got 3 other people. You're all working together. This is a big company. But to get those joint payoffs, you've got to be able to coordinate your actions. Well, exactly. I mean, the idea is you can look at what your payoff. You have to look at what your payoffs are, and you're trying to think, what's the benefit to me from either working hard or not working hard? Okay, and if everybody's decides to work hard, then if you're a blue player and say it's the blue player is everybody else, and you're the red player, if you work hard, your payoff's going to be 4. If you slack off, it's going to be 3, 2, 1. That's if everybody else works hard, okay? But supposing you're sitting up here at, no one else is working very hard, they're putting in a little bit of effort, but not too much, then your best response is to match their effort, which is not too much, okay? If you work too hard, you're going to end up paying all these extra effort costs, which are out of the endowment, which I gave you, okay? So the idea is your payoffs matter, and your effort levels matter, but you also got to try and figure out, what do I think other people are going to do? So if you think other people are, and we've got 3 other people, okay, you've never met them before. If the other people are working moderately hard, and they make that decision, and you decide to work quite hard, you're going to have to pay me 20 cents. Well, 2 units, which is 2 10-cent pieces, okay? On the other hand, they're going to, from their moderate hard levels, they're going to get 1. And if you had just worked 1, then you would have got 1 each as well. Okay? Now, yesterday when we did this, we paired this off. We didn't have any matching pairs. We had 2 pairs, and we had a 1 and a 4, and we had a 4 and a 0. And the person that had the 4 had to make a big payout, and the person that had the 0 got some extra money. Okay? So you have to decide. Okay, and I will pay out. Okay, so just have to think about it, and the rest of you try to think about, what do you think is going to happen in this game? Okay, just give you a minute just to think about it, and then make a choice, and then we'll kind of move along. Okay. And definitely talk to your neighbor a little bit if you've got a neighbor to try, because I'd like you to try and reason through what your thought processes were. There's a number of reasonable things to do in this kind of game. Okay, so Amanda, is it coming to you? Are you getting a flash of intuition what you're going to do? So if you got your choice? Okay, another 30 seconds, then you got to write it down, and Nathaniel's going to look over your shoulder, and he's going to make sure that you do what you said, okay? Oh, Amanda, Tara, sorry, I got that mixed around. I'm sorry. So what are you going to do? Okay. Are you okay about explaining your reasoning about that?
Yes, yep.
Okay, good. Well, so what are you thinking?
Well, I don't really care because it's only 40 cents. If it was chocolate bars, I might go less to try and make sure I got to keep them.
Oh, okay. What if you did care? Can I induce you?
I'd still go for it.
Even if they were chocolate bars?
Sorry?
I'll pay you in chocolate bars. I do have enough I don't have enough for everybody, but I do have enough, okay. Okay. Well, no, because, you can do that. You can sort of say, well, I'm going to take up on because I don't really care. But then what you want to do is think about supposing you did care and your payoffs were described in here. You're right. And I think that's the way often people play the games is that they've got their own payoffs rather than the payoffs that are supposed to be there. But that'll do it. Okay. So did you make a choice? What are you going to go for? Okay. Keep him to that, okay? Okay, Nathaniel, what did Tara write down there? Oh, Tara, you can tell him. We got a 3. Morgan, what did you do? You did a 4. Amanda? And Justin? Okay. So the first place, let me just make the payouts, okay? And just think about that. We got a 2, 2 4s, and a 3. Okay, so we got a moderate amount of effort. The minimum effort was 2, though, right? So let's see. Okay, the minimum effort's 2. So if you put in 4, then you don't have to pay me anything back, right? Because the minimum effort's 2, so the total output is going to be 4. And now how does this work? Did I get that right? Morgan put in 4. Okay, so the minimum, that's right. Morgan put in 4. The minimum is 2, so the total output is going to be 4. But his cost of effort is 4 as well. So his net payoff is 0. Okay, so he doesn't. That's what he would have to if he has his endowment. Which if the other guy had put in 0, he would have had to pay me some money. But he doesn't have to pay me any money in that one. Okay, and the same with Amanda. The same kind of idea is that the total output is determined by Justin's effort level, which was 2. Okay, so everybody gets 2 times 2 is 4, but then they have to subtract out the cost of their effort, which are, we had a 3 there as well, and so Justin should get 2 more, so I'll give you 2 more, okay, and Tara, you put in 3, right? So a 3 versus a 2, you should come up with another 1, again, because the total payout from the group is 4 per person, and you put in an effort at 3, so that's a net of 1 for you. So you get another. Okay, now Tara, what were you thinking about when you chose 3, or was it a total guess? Why did you think that? They're just poor payers. So you thought everybody else would be thinking, I'm not going to slack off. Okay. So why would you think that nobody else in this room wouldn't think about not working at all? Because if they expected everybody else not to work at all, then that would be quite a reasonable. Okay. Okay. Yeah. So they're going to put in some minimum level of effort. More. Okay. They could though in this game, right? Okay. Amanda, what were you thinking? Okay, so Amanda said that she didn't think the payoff was very exciting. What she told me is that she didn't care. And so that would be a slightly different game, okay, because what I want to do is change the payoffs to reflect the fact that Amanda doesn't really care about what she's getting. And then she said if they were chocolate bars, then she would care. I told her I would pay her in chocolate bars, but she said, no, I'm just going to stick with that, okay? So that's, though the payoffs that are up here are what I was hoping that she would act by, the actual payoffs that she had where it doesn't really matter to me. I'm just going to take it for and contribute to the group, okay, because I don't really care. So at the minimum, my level would be 4. Someone else might slack off, but I'm quite happy with that. Morgan, what were you thinking? Yeah. Okay, so Morgan is a philosopher, okay? And I noticed Morgan came out with 0 and Justin came out with 2, okay? So who's worse off? but I mean, relative to, but then it's worse off relative to what? Okay, and there were missed opportunities that could have come out from sort of coordinated effort here. Now, I hate to pick on you, Justin, because you were the slacker in the group here, but what were you thinking about with 2? Okay. Talk to me about this risk idea. Talk to me about this risk idea you were thinking about. Okay. Great. That's a fantastic explanation. Everybody hear that? What he's thinking about is, and the idea is to get the reason, just kind of listen to other people's reasoning and get the idea. There is a trade-off in this game. Morgan has it right in the sense that there's a number of things. Any of those 5 cells in the diagonal would be sort of reasonable to expect. Anything off the diagonal, according to the theory, we shouldn't really expect it. We still got a big problem: is how are we going to narrow it down even further? Okay, and then Morgan's thought was, or which could have been Megan's sort of thing too, is like, look at that 4 and 4. If everybody just focused in on those big aggregate gains that we could get together, if we all worked and coordinated our efforts together, we'd all be much better off than any of the other cells in there, okay? So that would be the idea of, okay, there's a number of things we can do. We can either end up with miserable payoffs down here where nobody's working but we're not getting any joint effort, or we can have great payoffs, but we've got this problem is nobody's talking with one another, communicating, enforcing agreements to actually sort of get up here. We've got to find a way of getting our expectations to converge on this one rather than that one out there. Now, it could be that everybody else is thinking 4 and 4, but it wasn't Justin. Because what Justin was thinking is, at least my paraphrase of it, is that suppose Justin's a red player, and he says, well, look, if everybody else has contribute 4, that's pretty cool. But if everybody else is thinking everybody else is going to slack off, and they decide that 0 is the best response to that, I'm going to be out my -4, a big cost. Okay? And so that's where the risk element comes in. It's like, this particular strategy is good if everybody else plays 4, but it's kind of risky if the minimum goes down. Whereas if you look at the safest strategy, that's to contribute nothing, because you get 0 all the way through, but at least you don't have to run any risk of losing something. Okay? So that's the kind of trade-off. Okay, I don't know how to connect in with the global warming yet. Okay, these payoffs are a little bit small for global warming, but the idea is the idea is to get a coordination. In particular, we're sort of thinking here of people working together. So like it might be if you're watching a rugby game and you got these defensive line and you got 5 or 6 guys and everybody has to hold their place. It only takes one. Okay, just to slack off just a little bit, and then the chances are the opposition will get through on that. So it's a team. It's kind of like the outcome is going to depend upon the effort of the minimum sort of effort involved, and that's kind of more rather than global warming thing. That's what we're thinking. The idea of pollution and other situations where there's it's like a prisoner's dilemma. Okay, but this isn't a prisoner's dilemma because there isn't any dominant strategies. But it's got that feature that it could be that the safest thing to do is for nobody to work, because that way you don't lose anything. So that would be another line of reasoning. Yeah. Well, okay, the question was, if you think of the other person as a competitor against you, you might, were you going to try and hurt them in some way? Yeah, you could try and do that, but then you'd want to change the payoffs. Okay, those would be like the outcomes of the game, but you're sort of thinking, I'm not so much interested in my payoff, I'm interested in smashing the other guy. Okay, which is okay. I mean, that's a different kind of strategy, a different game, but then you change the numbers to reflect that. So you're thinking, my best response is in terms of my preferences, which are, I don't really care what I get, but I want to punish that other guy. And I mean, look, that's the way people think, right? Okay, Jason, I'm sorry. He's a physicist, okay? Thinks we're all molecules, really nice to one another. We just bounce off one another. Sometimes we like to hurt the other people, okay? And the other thing is indifference. Amanda's thing is, well, it's like, I don't really care. The stakes are too small. If I was, if I don't have enough money, but if I was playing for like $10 for each of those units up there, then the stakes start to get, it's like, you don't want to, well, one thing, you don't want to lose out. If I was paying $10 per person for each of those, that's $40 to walk out of one lecture. That's not bad if you could get the coordination right. But if you get it wrong, you could be out $40 too. That would hurt, right? Fountain comes in, gives you $40, and you lose it because some guy plays it safe and plays zero. And you thought, well, if I put in a lot of effort, that's going to work really well. Okay? So that's it. I mean, the intuitive idea here, there is a bit of a trade-off in that if you don't coordinate it, it's risky. Okay, so then, Justin, I think your reasoning was kind of like that. And you thought you'd go for a middle kind of ground of 2 and 2. It's like, okay, if I'm a red player and I choose 2, I'm not going to get any big gains. But if people choose more, I'm still getting my 2 here. And I won't lose more than 2. And there's that kind of thought. Okay, so that's the purpose of this little exercise in the coordination games. Okay, now. When we go to a later part of the course, we're going to think about changing games. One of the reasons that management exists, and this is a big theory of kind of organizations, is that if the 4 of you were playing this game, you might actually hire somebody to make sure to watch what you all did and put in the effort level. Because if you all, well, I took it off the board there, but if you all put in the high effort level, you got a lot of good gains. And if one of you is kind of shirking, I mean, if you use that language, playing the zero, and the shirking isn't necessarily so bad like you're just slacking off. It's like just playing safe a little bit here. I don't want to lose out. I'm really risk averse. And so if you could hire some external, you could change the game to hire some external person to, you make these agreements. We're all going to work hard, and we're going to hire a manager to watch this. So we'll work hard, and we don't like having managers watch us work hard, but we also don't want to risk people shirking and us not making much joint output. And that's kind of a theory for the basis of organization, hierarchical kind of organizations where you empower one person to look at what other people are doing. You got a bit of a problem there because as soon as you introduce another player in the game, you wonder, what are their incentives? I mean, okay, like as an economist, I used to be kind of anti-union sort of things. This was just kind of my training, but unions can be very powerful. You get in a situation where you're the boss, the manager, is just doesn't take a liking to you and knocks you down. It's really nice to have some outside support there. Okay, and that's where the problem with the manager solution here is who's going to manage the manager. Okay, it works. Okay, and he gets layer on layer, but we'll talk about that more in chapter 10. Now let's the details of this stuff are not going to be on the exam, but I could give you a 5x5 payoff matrix and ask you to find the Nash equilibrium and explain your reasoning. Okay, even if it's not that particular game. Now, let's have a look at a 3-person prisoner's dilemma. I want to do this partly because it's in Chapter 4, which is on the exam. And this kind of game has it's a regular prisoner's dilemma. So what you're anticipating is each of the players is going to have a dominant strategy, and you expect them to play their dominant strategy. And when they do play their dominant strategy, if each of them didn't play their dominant strategy, they'd all be better off. Okay, but there's 3 players now. So let's just have a look at how you. This is explained in the text. If you, but let's run over it just to see how to look at these payoff matrices. Okay. So the way it works is you look at there's three people. They're trying to contribute to a common a project. In this case, it's keeping up their properties and having a nice garden, nice street to live on. And they can either contribute or not contribute. That's the red player, Emma. The blue player, Nina, can contribute or not contribute. And the green player can either contribute or not contribute. Okay? So the way this payoff matrix works is we assume on the left-hand side that the green player, Talia, contributes. And then you work out what the payoffs would be if Emma contributes and Nina contributes. So in this cell, if everybody contributes, they each get 5 and 5 and 5. Okay, 5. It's a big number compared to other numbers which are smaller. Okay, it's not bad, but it's not the best because if the other two are contributing to the gardens in the on the street and it's looking pretty cool, then if you don't contribute, your payoffs actually go up. Okay, so that's the temptation idea to deviate. You've got a temptation. Okay, and for Emma, no matter what the other players do, she's got this temptation. Like suppose that Nina doesn't contribute, but Talia does contribute, then 4 is better than 3, so don't contribute is better than to contribute. Similarly, if Talia doesn't contribute, 4 is better than 3, 2 is better than 1. Okay, so we can put in the best responses for Emma with these little X's. Okay, and it's just the idea, how do you work our best response analysis here? And you notice they all sit in the same row, so that, if you like, they're all the same strategy, so Emma's best response is always to not contribute no matter what the other players do. Okay. Similarly, let's look at how we'd look at Nina's situation. Well, Nina can either contribute or not contribute. That's if Talia contributes. Or she can contribute or not contribute if Talia doesn't contribute. So supposing Talia contributes, compare contributing with not contributing. Well, 6 is better than 5. Supposing that Emma doesn't contribute, it's just running through all the possibilities, okay? And the table helps keep those in mind. We're looking at the blue numbers, contribute or not contribute versus contribute. 4 is better than 3, okay? If we go over to the right-hand side, Talia doesn't contribute. Should Nina contribute or not? Well, not contributing has a 4, contribute has a 3. Not contributing has a 2, contributing has a 1. This is a bad outcome if you don't contribute, if you contribute, and Talia doesn't contribute and everybody else contributes. That's where you're the mug on the street. Okay, you're keeping up your garden, but they're not doing anything. And so you'd rather not contribute. So that's Nina's best responses. Now for Talia, I'm just going to put these stars in because the comparison for Talia is a little different, because what it says is supposing that the red player Ems contributes and the blue player Nina contributes, what can Talia do? Well, they can contribute or not contribute. So we've got to compare this green 4. Let me say that again. Supposing Emma contributes, Nina contributes. You get a payoff of 5 by contributing. If the other two players continue to contribute and contribute, you get a payoff of 6. So 6 is better than 5. Similarly, the idea is for each of the strategies of the other players. So what are the strategies of the other players? Contribute by Emma, don't contribute by Nina. That gives you a 3 if you do contribute, but a 4 if you don't. Remember, you're holding constant the contribute and the don't contribute when I make this comparison between the 4 and the 3. Similarly, looking at the 2 and the 1 and the 4 and the 3. And so the Nash equilibria becomes where everybody doesn't contribute, but there is this dominant strategy. I mean, if they didn't play their dominant strategies and everybody contributed, they'd all be better off. Okay, so that's a 3-person prisoner's dilemma. That's all we'll do for today. We have a little tutorial session tonight at 5 to 6:30. If you have any questions,